Hello everyone, myself Monishan Gowda. I'm currently studying in Sri Venkateswara College of Engineering, pursuing my electronics and communications. Today I'm gonna make a video on the subject computer organization and architecture. The today's topic is virtual memory. Virtual memory, expanding memory boundaries. Virtual memory is a memory management technique that allows a computer system to execute programs that are larger than the physical RAM available. It creates the illusion of having more memory than is physically present by using secondary storage, such as a hard disk drive, as an extension of RAM. This approach enables programs to access and process data that exceeds the physical memory capacity, overcoming limitations and allowing for efficient execution of larger and more complex applications. Physical memory versus virtual memory. Physical memory (RAM). Physical memory or RAM (random access memory) is the primary storage location for data and instructions currently being used by the computer. It is a type of volatile memory, meaning that the data is lost when the computer is turned off. Physical memory has limited capacity, determined by the size of the installed RAM modules. Virtual memory. Virtual memory is a technique that expands the perceived size of the physical memory by using secondary storage as a buffer. It enables programs to access more memory than is physically present, enhancing the overall performance and capabilities of the system. It is an abstraction layer that allows programs to run as if they have unlimited memory, despite limitations in the physical hardware. Address spaces and page tables. Address space. Each process in the computer system has its own virtual address space, a range of addresses that the process can access. This space is logical, meaning that the actual physical memory locations are not directly mapped to these addresses. The virtual address space can be significantly larger than the physical memory available, enabling programs to access more data than the physical RAM can hold. Page table. The page table acts as a translation mechanism between virtual addresses used by the processors and the physical memory addresses used by the CPU. When a process attempts to access a specific virtual address, the operating system uses the page table to find the corresponding physical memory location. This dynamic mapping allows virtual memory to efficiently manage memory resources by dynamically allocating physical memory to different processes as needed. Physical memory. Physical memory is the actual RAM available in the computer system. It is a finite resource, and an operating system manages the allocation of physical memory to different processes. Virtual memory uses the page table to translate virtual addresses to physical addresses, enabling processes to access more memory than is physically present. Page faults and swapping. Page fault. A page fault occurs when a process tries to access a page of data that is not currently loaded into physical memory. The operating system handles this event by interrupting the process, retrieving the missing page from secondary storage, and loading it into physical memory. The page table is updated to reflect the new location of the page, and the process resumes execution. Swapping. Swapping is a technique where the operating system moves entire processes or portions of processes between physical memory and secondary storage. This process is typically used when memory becomes scarce and the system needs to free up space for other processes. Swapping can be a time consuming operation as it involves transferring large amounts of data between memory and secondary storage. Demand paging. Demand paging is a technique that only loads pages into physical memory when they are needed, rather than loading all the pages at once. This reduces the initial loading time and memory overhead, but it can also lead to longer access times when a page fault occurs. Trashing. Trashing occurs when a system spends executive swapping pages between memory and secondary storage. This can happen when the available physical memory is insufficient for the processes running on the system. The result is slow system performance as processes frequently need to wait for pages to be loaded from disk. Demand paging and trashing. Demand paging. Demand paging is a memory management technique that loads pages into physical memory only when they are required. It is an efficient approach that reduces the initial loading time and memory overhead. As only the necessary pages are loaded, this strategy can lead to faster startup times and better utilization of physical memory. Page fault. A page fault occurs when a process attempts to access a page that is not currently loaded into physical memory. The operating system handles this event by interrupting the process, retrieving the missing page from secondary storage, and loading it into physical memory. The process then resumes execution. Trashing. Trashing is a condition that occurs when the system spends a significant amount of time swapping pages between memory and secondary storage. This can happen when there is an insufficient physical memory available for the running processes. The result is slow system performance as processors constantly wait for pages to be loaded from disk. Memory allocation strategies. First fit. Allocated the first available memory block that is large enough for the process. Best fit. Allocates the smallest available memory block that can accommodate the process. Worst fit. Allocates the largest available memory block for the process. Buddy system. Divides memory into blocks of equal size, allowing for efficient allocation and deallocation. Segmentation and paging. Segmentation. Segmentation is a memory management technique that divides a person's address space into logical segments, each representing a distinct part of the program, such as code, data, or stack. This approach allows for better security and flexibility as segments can be allotted and accessed independently. However, it can lead to external fragmentation if segments are not allocated optimally. Paging. Paging divides a processor's address space into fixed size units called pages, and physical memory is also divided into frames of same size. This approach allows for efficient utilization of physical memory, reducing external fragmentation. Paging is typically combined with segmentation to achieve a more comprehensive memory management strategy. Combined approach. In a combined approach, segmentation divides a processor's address space into logical segments, and the paging is then applied within each segment. This approach combines the benefits of both techniques, providing a more comprehensive and efficient memory management scheme. It allows for logical organization through segmentation while ensuring efficient physical memory utilization through paging. Virtual memory management algorithms. Clock algorithm. The clock algorithm, also known as second chance algorithm, is a page replacement algorithm that uses a circular queue and a reference bit to track recently used pages. When a page needs to be replaced, the algorithm scans the queue, marking each page as referred. Pages that have been used recently are marked as referenced, while older pages are not. The algorithm replaces the older page that has not been recently referenced. Recently used LRU. The least recently used LRU algorithm is a page replacement algorithm that replaces the page that has been least recently accessed. This approach aims to keep frequently used pages in memory and replace those that are less likely to be used in the near future. However, implementing LRU can be computationally expensive, requiring a mechanism to track the access history of each page. Optimal algorithm. Optimal algorithm is a theoretical page replacement algorithm that replaces the page that will not be used for the longest period of time in the future. This algorithm achieves the lowest possible page fault rate that is not practical to implement. As it requires knowledge of future page accesses, it serves as a benchmark for evaluating the performance of other page replacement algorithms. FIFO algorithm. The first in first out algorithm is a simple page replacement algorithm that replaces the oldest page in memory. It is easy to implement but can lead to poor performance if frequently used pages are replaced before less frequently used ones. This algorithm suffers from Baladi's anomaly, where increasing the number of available memory frames can lead to a higher page fault rate. Benefits of virtual memory. Larger program execution. Virtual memory allows programs to execute even if they are larger than the physical memory available. This enables users to run larger and more complex applications, expanding the capabilities of the system. Multitasking efficiency. Virtual memory enables the system to efficiently run multiple programs concurrently by sharing physical memory resources. It allows for better utilization of memory, as each program can access more memory than is physically available, facilitating multitasking. Reduced memory fragmentation. Virtual memory helps to reduce external fragmentation by allocating memory in fixed size units called pages. This approach optimizes the allocation of physical memory, preventing the fragmentation that can occur when memory is allotted in variable sized blocks. Limitations and challenges of virtual memory. Performance overhead. Managing virtual memory involves significant overhead. Page faults, which occurs when a page is not in memory, require the operating system to retrieve the missing page from secondary storage, leading to performance degradation. The page table also needs to be maintained and updated, adding to the overall overhead. Crashing is a condition that occurs when a system spends excessive time swapping pages between memory and secondary storage. This can happen when the available physical memory is insufficient for the running processes, resulting in slow system performance. Security concerns. Virtual memory can pose security concerns if not implemented properly. Malicious software could potentially exploit vulnerabilities in the virtual memory system to gain access to the sensitive data or compromise the integrity of the system.